Hi, and welcome back. I wanted to show you a project that I'm doing on the side of my VHDL studies. Um, and to learn VHDL, the best thing to do is to make some code. Okay, we have a lab, but I'm at the university, but I'm going to do some on my own. But first I thought I'm going to show you the state of the C64 Saver project. And for those of you who don't know what that is, it's this device here. Uh, it has a red and green LED, and you plug in the power supply here, and then this one into Commodore 64, and it switches off when the voltage is too high. I have received a device which is it's not working. It's going to red at once, even at normal levels. So I will dissect this one and try and find out what's wrong. So the customers told me that maybe had connected the wrong pins in here and then fried it, but I don't think you can do that because I have tried the wrong polarity here and it doesn't harm it at all. And if you look at the circuit diagram, it doesn't make sense to be able to harm it, so I think maybe it has been banged down in the post, maybe. It's very, very, very hard, this shell here. So, uh, so I can tear that down quickly and let's have a look. If it's, I can't see what's wrong with it. Yes, this guy went straight to red, but now I replace those two guys over there. Which are these two? Sorry. And I measured voltages, and the thing was that the voltage regulator didn't manage to everything was right here, but when I came over here it wasn't correct anymore. So and also on this side, when the voltage went up, this started to conduct on this side, so something was short-circuiting or something. So there was two faults, both here and here, I think. So because when this voltage went down, this one didn't pull all the way up. So I switched both of them and then it works. So I'm confident that something has happened to those. Maybe it's electrostatic discharge, I don't know. Or it was the faulty components. But if both of them was wrong, then yeah. And here I have made 20 new boards using the solder paste that I bought, and I will link in some video right now. Not link in, I will add it as an overlay so you can see what happens. So yeah, so this is solder paste, and also I have this Amtech flux, which smells really bad, but yeah, you just have to ventilate. So it was really nice working with it. It's faster using the iron. I must admit that I didn't like the way these SO8 packages was soldered, so I had to rework them and add more tin. So I don't know if it's the packages or what, or if it's the way the pads are designed, because they are rectangular. You have the two LEDs on the bottom there, and I can tell you, I put all the LEDs out on the lay them out such that I can just pick them, and I use the meter in diode mode to find the direction of the diode, and then after doing that for 20 LEDs and soldered up, for some reason I don't know what happened, but all of them was wrong way, so I did something systematic at least. So that was boring though, because I had to fix that. You can see the soldering is quite nice, and I also soldered this board using this technique. You can see how nice it looks around all of this 0603 size components. I had to do some rework here though, because my circuit was wrong, unfortunately. So yeah, enough about that. So let's continue to the... Oh, yeah, maybe I should dissect this one first. Let's see what's going on here. So, well, I'm trying to open this one. It's really hard. The customer told me that maybe I'd done the wrong polarity, as I said earlier in the video. And I said, no, I don't think so. There must be something else. And I said to him, okay, I'll send you a new one, and if you have got time, please send it back. I didn't want him to bother him if it was too much hassle to send it back. So yeah, so now I'll stop the video. But he sent me back, so I can check it out. And said I will pay the postage. So let's see, so what I'm suspecting is these two guys here. Another thing it can be is flux underneath these two. I had problems with that before, so but the soldering looks nice here, so, and I can't see any cracks. So at the moment I don't know what's wrong with this. I have to investigate that further. So I have sold like I don't know how many, but I've been selling these for like a year, so, and this is the first one which comes back. Yep. So this is the code, and I have two codes. I have one for timer and one for TB timer. I will get into what that means, and I will use a program which is called I'll just record a screen now. So it's called Model Sim, and yeah, it's a program where you can simulate your design or your models. So VHDL, it's always has an entity and an architecture. Yeah, so this is my VHDL code and the project I'm practicing on, and also this is the Commodore document, which, as we know, Commodore wasn't really good at documenting what they did, so this can be inaccurate. So, but let's just hope it's not too inaccurate. So, I was discussing with Gadget UK that we do a microcontroller based CIA, but there's a problem with that when it comes to timing, and Maybe I can talk about that some other time, but I thought maybe this would be a cool project because the complex interface adapter, or the CIA, isn't that complex. You can see the block diagram here. It's very small, but you can see here you have the data bus and you have a chip's access control, and then you have all these little modules. So what I've started of doing is trying to make this little peripheral model over here. So it has a control register and a timer register, and I'm thinking I'm going to use this chip's access control to sort of communicate with it, such that when you get a chip select and a read write, it will then fire a write to it, or if you get a chip select and read, it will fire a read. And also here you can see the register select, so you only have 4 bits of select, and then you can have an address. So you only have 16 addresses. And if you look at the document, there's a lot of description here. So I started with the timer part, and here you can see those registers. You have timer A low register, which is a bit it's actually the value which the timer gets if you load it. So it's not perfectly written there. And here you have the control register, which is also associated with the timer. So I started off just having a timer decrementing, because the timer is a decrementing value, and I had it start and stop by just looking at this bit. So, and I did that, and that was really cool. So let's see what I've done. So in the VHDL code, this is not like programming a software, but it does look a little bit like software. So like here you have it has sequential statements. It's not sequential in that regard that it every line is executed like in software successively, but what comes first in this list is or last is the one that is used. So what you actually is describing here is a piece of hardware. So, and right now I'm simulating without a target device or a FPGA. So this is just abstract. So just it's like a class. This is describing what the... If you think about Java, you make classes, and you can't use classes on their own. Well, you can have functions in them, but if you look away from that, you can describe a data object which is put into memory when you instantiate them. And that's what I'm doing over here. I'm telling the VHDL that I want an entity, and that entity has a set of inputs and outputs. And when I have said that, you have to say what kind of architecture that entity has, and the architecture will describe the behavior of that model or that entity. So over here, if you take the Java analogy, you have an instantiation down here. So I instantiate the timer from my work library, and the RTL is the architecture name. So we can instantiate, just like you write some variable equals new, and then the class name in Java. And also when you have a entity, there's a lot of repetition in VHDL also. You have to repeat the port. So that's what I've done. So, and the reason for that is that you give them names, and those names are in this scope, and when you instantiate, you do a netlist, and what that means is that you connect the names you have in this file with the names on the port. So yeah, so let's move over to the architecture. This is not about VHDL, but just to have an initial explanation of what's going on. In the architecture, you first declare the signals you're going to use inside this model. So what I've done, I have made a few signals, and those are registers. And this double, this means comment. So that means that this line is not going to be used. So here we have a register, the load register, timer latch load value low. So it's a 16-bit timer, so therefore you have two 8 bits. And down here you have the 16-bit timer, 15 down to 0, that means 16 bits of a unsigned type. And when you have declared all of that, that was the first thing I did. I want to see if I could actually write to them. And to write to them, I have to be able to listen to the clock, I think, and then the write pin, and then I'll have to also listen to reset, because it has to be reset sometime. And there's several ways in writing statements. This is a so-called concurrent. That means that it happens at the same time. Let's say if I say reset equals 0, I can't do that right now, but let's say I could that. These two lines are executed simultaneously, or it's not executed. It's hardware. So you get two pieces. You get two drivers. You get one driver which drives RRQ, and then the other one drives reset N. So the reason why I'm saying that RRQ is 0 is because I haven't built this part of the code yet. So it's just saying 0 all the time. And then the other thing you can have sequential statements. Then you have to open a process. So every process are parallel, 100% parallel process. So this is a write register. This is one process. That's one piece of hardware or circuit, and this is another piece of circuit. So yes, so the first thing I do is that I have a process which listens. It has a sensitivity on phi2 or reset N. So some of these has to be changed before this process wakes up. So, and if there's a reset, then this process wakes up and it checks if it's 0. Then it does all this. It changes all of these signals to 0. If it's not 0, it looks if there's a rising edge on the clock, and if there's a rising edge on the clock, we will then we can skip this part. We will check if the write bit is 1, and if it's 1, then we know it's going to write something, and then it checks the register select, which we had on the address bus, or if you look over here, we have the over here, the chip control, and then it looks what pattern that has. So if it's a 0100, then we want this register to get the data input value into TA low. So this is a casting because it has a different, the DI is a different type, so never mind. And then all the individual bits in the chip control register A for timer A. If it's this pattern in register select, then it will set the individual bits on that one. So this is really fast, and yeah. And as I explained, maybe in another video, I don't know, remember when I said it. Anyway, some of these bits they have. Yeah, that was a comment to Catch It UK. These register bits, individual just register bits. If you do a load, nothing is actually stored. It says in the datasheet. So if I go down to sorry for all the flickering here. If you see here, if I start the timer, this bit is automatically reset when underflow occurs during one-shot mode. So basically what that means is that if you have one shot, it means that the timer will go to 0. 5, 4, 3, 2, 1, 0, and when it goes to 0, the timer should stop. So that means that this bit will reset. And that's what I'm doing here. So if it's in one-shot mode, that means one-shot mode, and the timer is 1 before 0, that's a problem you have. You have to check right before. Then I stop the timer here. So yeah, sorry for scrolling too far. So but I think I have to scroll up now. So this is the timer part, the process, and here you can see that the timer is decrementing for every rising edge of the clock. And if you have a load from the load register, then you will load the timer with these two registers. This is the high part and this is the low part. It's so easy to write this. So, and that's basically it. So what about the start and stop? Well, that's here. The timer will only decrement if the CRA start is 1. So that's it. So let's simulate it. That's the fun part. So the first thing you have to do is to compile your code, and then so this is Model Sim, the student edition I'm using, and also have to display the compiler output to get any compiler output, and everything is okay. So what you can do that then is to start simulation. Then you select your test bench. I haven't talked about the test bench. Yeah, so to simulate this model, you have to put stimuli on these pins, and then you can observe the outputs and the internal state of the registers. So what I did is made a test bench with an entity which has no port pins. It's normal. And then I describe the behavior of that this test bench, and this is the instantiation that I've talked about, which this just describes the port first, and the signal I'm going to put stimuli on, and then I instantiate the timer and connect. This is a netlist actually, so that you connect up all of the signals, internal signals, with the signals on the port. Then I need a clock. So this doesn't make sense in hardware, saying wait for 500 nanoseconds, but in the simulation it makes sense. So this process just repeats and repeats forever, so you get a clock at 1 megahertz. And then you have a concurrent statement. Remember, this is sequential and this is concurrent. That means this happens the same time as this happens. So So we set that the reset is 1 to begin, and then it goes active after 1 microsecond, and that's 1000 nanoseconds, and then after 2000 nanoseconds it goes off again. And we send write pulses at different intervals, and we do read pulses, and count at the moment we are ignoring because I haven't finished the program. And then you can see we do the row select, so I select several registers at several times. For example, I select this register, which was low, and then we do a write here. At the same time, we have to set the data input for that module. You see here we have data input, and we feed in some data, just some data. So enough about that. Let's just look at the simulation. So we're simulating the test bench like this, and then yes, and I will now close this down a little bit so we can see what's going on. So before doing anything, we will add these signals. So these are the port signals, but we will also, something I found out yesterday, we will add some internal signals like the registers. So, and here's the timer. Let's see, add wave. Let's see if I can make this window a bit smaller. This, maybe I can, yeah, there you go. Now you can see all of them. So what to do, you just write run for how long you want, let's say 70 microsecond, boom. And if I now, I can make this window bigger, so paired, yeah, zoom full. So there's a lot of stuff happening. So you can see the timer clock over here, the phi2, which is like, if you click here you can see it's like 1000 nanoseconds. And the first thing I do is a reset. I apply a reset, and then you can see all the registers down here. The start, PB on, the TI low, TI high, it goes to 0. So this is the stimuli and this is the behavior. So now we are observing that it actually works. It actually does a reset. So the internal state, the internal signals are now reset. Okay, so we're done with the reset. So we get over here and we put some data on the data bus just to see if we can actually write something in on the registers. And we also have to set the address where those data is going. So I set the data to be the address to be hex 4, and that's the TA low register. And then there comes a write, and you can see the internal state of TA low is actually taking that data, so that's working. And then in the next state here we do 0 0, so I'm going to write to the highest part of the TA low on the address 5, hex 5, and that's 0. It was 0, so you don't see any change here. But trust me, it does change. And then I write to the control registers, which is on E, and I write this bit pattern here. And you can see that when this write comes, you can see that the serial start is 1. And down here you can see the timer. So the timer was reset to begin with, but when it gets a 1 on that bit, it starts counting. So we can zoom in a little bit on that. You can see that it starts counting, and it also has a load. And what does it load? Well, let's have a look at the code again. Here, if it has a load on the rising edge, it will then copy whatever is in these two registers here. So let's get back. So we can see that TILO is 000. Oh no, it's 4, and the high bit is 0. So you can see that it gets a 004. So here's the clue though. Is this counter supposed to start at this clock cycle or this clock cycle? I don't know. So maybe this is wrong, but it's only one clock cycle. Maybe it's not correct. So, but anyway, it's a start. And you can see that the clock is decrementing. And what about the run mode? The run mode is 1, and if the run mode is 1, then we are in one-shot mode. That means that this start bit is going to automatically be reset when an underflow occurs. And does that happen? Yes. There you can see the start bit. Sorry, the start bit goes to 0 when the timer goes to 0, and also it stops the timer. As you can see, just a flat line over here. So yeah, and that's one thing I wanted to test, if it actually stopped. And I also wanted to try and stop it manually by writing to E AA and do a write, but actually I have to change the code to see if that's actually working. Then I have to change the run mode, which is over here. Just have to trust me on this one. So, because that's bit 4. So if I set that to 0, then it's in continuous mode. Then we have to stop it by writing to the register instead. It's not automatically anymore. So what we have to do then is can you come in? You have to compile it. So now you say a question mark. So when you come in, so you have to compile it, and then you have to restart. Ingrid here. And try the simulation again. And now I have to go back to the wave and see what happens. And now you can see that the... Oh, actually I flipped the wrong bit. I flipped the load bit. It was the run mode. Okay. Well, that's interesting also. You can see that it no longer loads that TALO value 4. It's 0 to begin with, and then it goes to F, and down. So, but interestingly, you can see that it also stops when I write a, let's see here, writes a 0 on the start bit. That's what's going on here. We are on register select E. That means this control register, and the timer stops. So, and I also tried another thing, and that was reading back from the registers and see if I get some data out. And that seems to work also. You can see that I get data out here. So that's what I've been doing, and I'm still learning, so this is probably not the way to do it. So this is the workflow. You start just working without the target device, so just making an abstract model And then we'll try and do the same simulation for the device and see if it actually fits. And normally you make a test bench for every module that you make, so you can verify that it works as you want it to work. So I think it's very interesting. You can see there's a lot of bits there, so I have a long way to go. And this is only one part of the whole block diagram. So that's timer A. You can also see that timer A can control timer B. So yeah, and also there's the interrupt, and there's a flag, and time of day, and serial port, which I don't have a clue how it works. So yeah, so I'll have to ask for help then. And you have also the general purpose IOs, which has a direction. You say which direction the data goes. You can write to them and read from them. And everything is controlled by this axis over here. So yeah, so that's what I wanted to tell. So thank you for watching. Just ask questions in the comment field. Thank you.